Imagine for a second holding like a modern wireless pacemaker right in the palm of your hand.
Oh, yeah, they're incredibly small now.
Right, they're tiny.
Yeah.
And inside this tiny piece of hardware, which, keep in mind, is designed to be implanted directly into a human chest cavity, you basically have two main things. You have a microchip doing the thinking and an antenna doing the talking.
Exactly.
But here's the question for you listening. What if you're a developing nation that doesn't have, the $20 billion required to build the mega factory that manufactures that microchip?
Which is most nations, honestly.
Yeah. So today we're looking at a strategic blueprint that suggests you don't actually need to build the factory at all. You just need to own the antenna. We are taking a deep dive into an exclusive interview with Dr. David Nghiem, and this was published in the special edition on innovation and digital transformation, or Sanctao Vatuendoiso.
It's a really fascinating piece of media.
It is. And accompanying this interview, we have access to this whole stack of technical schematics and like laboratory photographs that outline what is basically a highly unconventional, low-cost backdoor into the multi-billion-dollar global semiconductor race.
Yeah, and that race is, I mean, the global semiconductor and AI supply chain is essentially this heavily guarded fortress right now. You have these massive entrenched economies pouring just unprecedented capital into fabrication plants.
The fabs, right?
Right, the fabs. And they're doing that just to print silicon at scale. So for an emerging economy like Vietnam, for instance, securing a position in that ecosystem is, well, it's a critical national ambition.
But competing head-to-head on manufacturing volume with the established giants is, it's virtually impossible.
It really is. The capital barrier to entry is just insurmountable. But the materials we are examining today, they provide this really fascinating counter-strategy. It pivots away from manufacturing volume completely, and it focuses entirely on securing a highly specific intellectual property bottleneck.
Okay, let's unpack this. Because this is where Dr. Ngiem's interview proposes a massive paradigm shift for you to consider as you listen to this. He's basically arguing that a developing tech sector shouldn't even try to build the whole fortress.
No, not at all.
Instead, they should find this narrow, highly specialized, high-value niche and just establish absolute dominance right there. And the specific niche he targets is antenna technology.
Which I know sounds a bit funny at first.
It does, because on the surface, it sounds almost retro to someone following like cutting-edge AI. People hear the word antenna, and they often picture, a telescoping metal rod on an old 1990s boombox.
Yeah, pulling out the silver rod to get a radio station.
Exactly. Not like a cornerstone of modern digital infrastructure.
Right, but the reality of modern antenna engineering is incredibly sophisticated. And actually, its invisibility is exactly what makes it such a strategic blind spot.
It just blends into the background.
Exactly. To truly grasp the value of this niche,
Yeah.
we really need to look beyond that basic function of just receiving a radio signal. We have to examine the physics of modern device communication. We aren't just talking about a passive piece of metal anymore.
No, it's so much more than that. I was trying to think of an analogy for this, and it's like, okay, if the semiconductor chip is the brain of a smart device, then the antenna is the mouth and the ears.
Oh, that's a perfect way to look at it.
Right, because a genius brain is totally, completely useless if it can't actually communicate with the outside world.
Absolutely. The engineering required here is, it's akin to complex acoustic engineering in a world-class concert hall. You have to literally shape the signal, direct the waveform, and manage all the physics of electromagnetic propagation. And you're doing this within microscopic environments.
It's wild to think about.
It is, because you can have a state-of-the-art processor operating at billions of cycles per second, but it is entirely isolated from the network without a perfectly tuned antenna array to translate those electrical impulses into radio frequency waves.
And the source material actually illustrates the sheer volume of these arrays brilliantly. There's this top-down schematic of a standard modern car provided in the document.
Oh yeah, that diagram is eye-opening.
It really is. It maps out the vehicle's communication architecture, and it uses these little blue dots for the exterior antenna nodes and red dots for the interior ones. On the exterior alone, you're looking at nodes integrated into the front and rear bumpers, the roof spoiler, the outer mirrors.
It's even the glass, right?
Yes, embedded directly within the glass of the windshield. And then when you move to the interior, the red dots are just clustered everywhere across the dashboard. They're tucked into the structural pillars. They're distributed throughout the whole cabin. It essentially turns a standard passenger vehicle into a rolling, high-density network hub.
And see, that diagram highlights the absolute engineering nightmare of what we call co-site interference.
Co-site interference.
Yeah, because a single vehicle today relies on dozens of highly specialized antennas simultaneously. You've got radar for collision avoidance, GPS for navigation, satellite receivers.
Right, the cellular modems.
Exactly, modems spanning multiple frequency bands, plus your internal Wi-Fi for passenger devices, and low-frequency Bluetooth or NFC for your keyless entry. Every single one of those systems is actively broadcasting and receiving electromagnetic radiation.
All at the exact same time in the exact same car.
Exactly. So the engineering challenge is ensuring that the GPS signal, which operates at roughly 1.5 gigahertz, isn't completely jammed by the internal Wi-Fi router that's broadcasting at 2.4 or 5 gigahertz right next to it.
Wow, yeah.
Each antenna must be meticulously designed to basically filter out the noise of its neighbors.
And the sources expand this necessity into the medical sector too, which is where the stakes obviously elevate from, dropped calls to literal life and death.
Right, going back to the pacemaker example.
Yeah, the interview details the engineering behind those wireless pacemakers. The antenna inside that device has to transmit a clear, reliable signal through human muscle, through bone, through fluid, which, by the way, are notoriously hostile to radio waves.
The human body is a terrible environment for RF signals.
It really is. And it has to punch through all that to connect securely to a patient's monitoring smartphone and simultaneously to a doctor's remote diagnostic system. And it has to maintain that connection flawlessly, even if the patient is like standing right next to a microwave oven radiating electromagnetic noise in their kitchen.
Which raises such an important question about the intersection of different tech sectors. Specifically, how the rigorous standards of one field can dictate the baseline for another.
How do you mean?
Well, when an engineer solves the problem of signal attenuation through human tissue without increasing the power draw to a level that just kills the pacemaker's battery.
Right, you can't just crank up the power or the battery dies.
Exactly. When you solve that, that breakthrough in efficiency immediately becomes highly lucrative intellectual property for consumer electronics. The ability to optimize and focus waves, which is a technique known as beamforming, rather than just indiscriminately blasting radio frequency energy in all directions, that is critical for next-generation Wi-Fi and 6G cellular networks.
Because it's just so much more efficient.
Right. The demand for this level of bespoke, highly efficient antenna design is completely ubiquitous across every single sector that utilizes wireless communication.
Okay, I have to inject some skepticism here, though, because I get it. I understand the demand is massive. But I really need to push back on the premise that this is just an open lane for a country like Vietnam.
A fair point.
Because we are talking about a global tech industry where massive conglomerates have literal armies of PhDs working on wireless standards. And according to the interview itself, Vietnam currently operates mostly at the assembly level, right?
Yes, mostly.
They import these components or they assemble the devices for foreign companies. They don't actually own the core IP. So how does an emerging market realistically leapfrog legacy tech giants to control such a foundational piece of hardware design?
What's fascinating here is Dr. Nghem's assessment of the structural vulnerabilities within those exact legacy systems. He points out that while the massive foundries are locked into this relentless, hyper-capital-intensive cycle of shrinking silicon transistors, antenna design is inherently custom.
Oh, because every device is different.
Exactly.
Yeah.
You cannot just stamp out one universal antenna design because the performance of an antenna is entirely dictated by the physical dimensions of the specific device it's going into, the materials surrounding it, and the specific frequencies it needs to handle.
So it's not a one-size-fits-all thing.
Not at all. And furthermore, he identifies that the domestic competition within Vietnam regarding core foundational antenna design is currently minimal. They do not have a bloated legacy telecommunications design industry holding them back or, demanding adherence to outdated methodologies.
So it is a totally blank slate for them.
Yes.
Which allows them to build for the absolute current state of the art rather than retrofitting old infrastructure. And I have to say, the capital required to build that foundation is probably the most surprising detail in all these documents.
The cost is shockingly low.
It is. The interview explicitly lays out the action plan. Skip the massive fabrication plants entirely for now. Focus exclusively on building an advanced antenna design lab. And the price tag for outfitting this lab, it's cited at under 1 million US dollars.
Which is nothing in the tech world.
Nothing. In a sector where tech investments are routinely measured in the tens of billions, a sub $1 million entry point to secure foundational IP is almost absurdly low.
And the economics of that initial step are highly strategic because you are investing in testing equipment, you're investing in simulation software and human capital rather than,
Yeah.
heavy manufacturing machinery.
Right.
And Dr. Nghiem maps out exactly how to monetize that lab immediately. He suggests targeting RFID technology first.
Radio frequency identification.
Yes, this is essentially the backbone of modern logistics. It's used for tracking inventory in warehouses, managing supply chains, automating toll booths, you name it.
But why start there? I mean, why not jump straight into smartphones or 5G towers if your ultimate goal is to dominate the global market?
It really comes down to the physics of the learning curve and capturing immediate market share. See, Vietnam currently imports a vast amount of RFID technology just to support its own booming manufacturing and export logistics sectors.
Oh, so they are already buying a ton of this stuff anyway.
Exactly. So by utilizing this new lean design lab, Vietnamese engineers can begin designing specialized multi-frequency RFIDs that are tailored specifically for their domestic market. More specifically, starting with low frequency or highly specialized high frequency RFID is brilliant.
Why is the low frequency part so brilliant?
Well, low-frequency radio waves penetrate liquids and metals far better than ultra-high-frequency waves, which makes them absolutely crucial for tracking agricultural goods or metal shipments. And both of those are huge industries in Vietnam.
That makes total sense.
Yeah, it's a highly profitable market with immediate built-in domestic demand.
So the strategy is basically to secure the intellectual property of the design first. You engineer a better, smaller, more efficient RFID tag for the local supply chain. And because you own the blueprint, you don't actually need the billion-dollar factory to print it, right?
You can just outsource it.
Exactly. You simply outsource the physical manufacturing of your proprietary design to existing foundries overseas. You capture the profit margin of the innovator rather than the really tight margins of the assembler.
Spot on. You master the feasible, high-margin steps first to build your capital and your expertise. And then, once you dominate the local design market and the scale warrants it, you can eventually consider bringing the physical manufacturing in-house. But the true leverage in the modern tech economy always resides with the entity that holds the patents on the design.
Here's where it gets really interesting, though, because capturing the local RFID market is a great foundation, sure, but it isn't going to force global tech giants to suddenly alter their supply chains to work with you.
No, it's just a stepping stone.
Right. So to do that, the source material introduces a technological leap that goes far, far beyond standard RFID. There's a close-up schematic of a technology developed by Talented Minds Agency, or TMA. The acronym is RFICWA,
Yes.
and that stands for Radio Frequency Integrated Circuit with Antenna.
And looking closely at that schematic, it reveals just a monumental shift in hardware architecture. The visual shows this microscopic rectangular semiconductor chip. But instead of the antenna being a separate, discrete component that has to be wired to the processor on a printed circuit board.
Which is how it's normally done.
Right, normally they're separate. But here, the antenna array is integrated directly onto the surface of the silicon microchip itself. It is literally a microscopic maze of conductive material layered right onto the silicon die.
The audacity of that design is striking. But again, I have to ask, if integrating the antenna directly onto the silicon is the holy grail of hardware engineering, why hasn't everyone already done it? What are the actual physical hurdles that are stopping the biggest players from just doing this?
Well, the physics of putting an antenna directly onto standard silicon are incredibly hostile.
Hostile how?
So, standard silicon used for processors has relatively low electrical resistivity. When you try to blast a radio frequency signal through an antenna that is sitting directly on top of it, the silicon substrate literally absorbs the electromagnetic energy. It converts your data signal into wasted heat.
Oh, wow. So it basically eats the signal.
Yes. And furthermore, the processor underneath is operating at billions of calculations per second, which generates a massive amount of electromagnetic noise. If you put the antenna right on top of it, the thinking of the brain completely grounds out the talking of the mouth.
I see.
Historically, engineers had to physically separate the two components just to achieve impedance matching and isolate the signal.
So TMA's RFICWA technology represents a solution to those exact physical bottlenecks then. They've engineered a way to isolate the antenna from that noisy, absorbent silicon underneath. Whether that's through novel substrate materials, or micromachining, or advanced geometric shielding, they've figured out how to allow the two components to coexist in the same microscopic footprint.
And by solving that substrate loss and interference problem, you eliminate the physical distance between the processor and the antenna. You drastically reduce signal loss along the connecting wires, you lower the overall power consumption of the device, and most importantly, you shrink the physical footprint of the entire wireless module down to the size of a grain of rice.
That's unbelievable.
It is. If a newly established design lab in Vietnam can master the baseline RFID phase and then scale up to fully command this direct-to-chip RFID integration, they hold an ultimate trump card.
Right, because everyone would want that.
They can walk into the procurement offices of the largest automotive, consumer electronics, and defense contractors in the world and offer a proprietary component that makes every single one of those companies' future products smaller, faster, and more power efficient.
The scale of that pitch is just enormous. But, a blueprint is really only as credible as the architect who drafted it.
Very true.
So to understand if a developing nation can actually execute this sub-$1 million pivot into the center of the global semiconductor industry, we kind of have to examine the guide behind the vision. And the source materials dedicate significant space to the credentials of Dr. David Ming himself.
And synthesizing his professional background really reveals why this strategic roadmap is grounded in rigorous empirical engineering rather than just being, high-level economic theory. The photograph included in the documents provides a perfect visual anchor for his methodology, too.
It is a really striking image. He's seated in a specialized anechoic chamber, and for those of you listening who might not be familiar with that, this is a highly controlled testing environment where the walls, the floor, and the ceiling are completely covered in these massive wedge-shaped spikes made of radiation-absorbent material.
They look kind of like giant blue foam pyramids.
Yes, exactly. And these spikes are designed to completely absorb electromagnetic waves, preventing any signals from bouncing off the walls. It basically creates a free space environment, completely devoid of outside radio frequency interference or internal echoes.
Right.
So he is sitting in the center of this visually intense, deeply silent room, holding a mobile phone, and he's measuring the absolute true radiation pattern of its antenna array.
That environment demands absolute precision, which aligns perfectly with his career trajectory. As a Vietnamese-American scientist, he has operated at the highest echelons of both academia and industry.
He has a really impressive resume.
He does. He served as the vice president of the Cullen College of Engineering and directed the Telecom Center at the University of Houston. And then moving into the private sector, his footprint covers foundational engineering work deep within corporations like Harris Corporation, Qualcomm, and Medtronic.
Oh, Medtronic, wow.
Yeah, and he holds 17 distinct U.S. patents that span semiconductor architecture, telecommunications infrastructure, and advanced antenna design.
And his work with Medtronic specifically bridges that gap we discussed earlier, right? Between telecommunications and life-saving medical devices. Because the sources note that in 2016, he was recognized by the IE, which is the Institute of Electrical and Electronics Engineers, basically the preeminent global authority for this field, and they gave him their Outstanding Engineer Award.
Yeah, and that award specifically highlighted his pioneering contributions to wireless medical applications. He was absolutely instrumental in developing MRI-safe technology.
Oh, wow.
Yeah, he engineered device architectures that can withstand the extreme magnetic fields of an MRI machine without failing, and more importantly, without causing thermal injury to the patient.
That's incredible.
He has also developed highly sensitive biosensors for detecting skin cancer, alongside highly efficient wireless charging technologies for implanted devices.
There's also this distinct piece of historical verification included in these files that I found fascinating. It's a scanned archival letter dated December 2nd, 1999. And it is from then Vice President Al Gore, written directly to Dr. Nghiem during his tenure as the CEO of USA Wireless. And operating strictly as an objective historical record here, the letter explicitly thanks him for his efforts in improving telecommunications accessibility and consumer safety.
It's a great piece of historical context.
It is, because it acknowledges that his technological insights were directly helping to streamline how the national infrastructure served its citizens back then.
Right, and providing that document establishes this 30-year track record of his technological innovations actively shaping practical, national-level telecommunications policy and infrastructure.
Right, he's been doing this a long time.
Exactly. He is not an academic dealing purely in theoretical models. His designs have survived the rigors of mass commercial deployment and heavy federal oversight.
Which makes his actual offer to Vietnam so significant today. This deep dive isn't just an analysis of an interview, it's an examination of an active technology transfer. Through his agency, TMA, Dr. Nghiem is proposing a direct bridge. He isn't just handing over a schematic and walking away.
No, the practical execution of this roadmap relies entirely on that bridge. TMA is actively connecting Vietnamese institutions with engineering professors in the United States to establish a curriculum that matches global standards.
Getting the education piece in place.
Yes, and more critically for the immediate timeline, TMA is offering to supply the initial teams of veteran engineers for the first 1 to 2 years.
Oh, wow. So they're bringing the talent right to them.
Exactly. They're providing the human capital required to ensure this new design lab bypasses that typical trial and error phase and begins generating viable IP immediately.
He is bringing his patents, his veteran personnel, and his decades of institutional knowledge to essentially jumpstart an entire sector. But the documents heavily emphasize that this is a highly time-sensitive maneuver.
Very time sensitive.
He believes that if they accept the training, outfit the lab, and move aggressively, Vietnam can establish a permanent, recognized position in the global antenna industry in just a few short years. But the window to exploit this specific blind spot in the market is closing fast, as the major foundries continue to consolidate power.
And if we connect this to the bigger picture, the urgency makes perfect sense when you look at the trajectory of the hardware itself. The evolution of technologies like TMA's RFICWA, that direct microscopic integration of the antenna onto the silicon die, it signals a fundamental shift in how the physical world operates.
How so?
Well, if the industry successfully mitigates that substrate interference and antennas continue to shrink until they are just a standard microscopic layer on every single processor produced, the physical and economic barriers for any object to become a smart device completely vanish.
So, what does this all mean for you as you absorb this strategy today? Whether you are mapping out your own career trajectory, looking for a competitive edge in your startup, or just analyzing how entire national economies pivot to survive, the core lesson here is the asymmetric power of the high-value niche.
It's so powerful.
You do not always need the capital to build the entire car or the $20 billion factory to print the silicon brain. Sometimes aggressively identifying a blind spot, understanding the physics of why an invisible antenna is just as critical as the processor it serves, that is enough to make you completely indispensable to the giants who do build the factories.
And the consequence of mastering that specific niche is a total transformation of our environment.
Yeah.
When the processor and the antenna are fused into one microscopic, hyper-efficient unit that costs literally pennies to produce, we move way beyond smartphones and smart cars.
Right, it goes everywhere.
We enter an era where a standard adhesive bandage on your arm has the processing power and the transmission capability to monitor your vitals and alert your doctor to an infection before you even feel a fever.
That is mind-blowing.
Or a world where the structural concrete in a bridge can wirelessly report microfractures to a city's maintenance grid on its own. Mastering the back door into the semiconductor industry accelerates a reality where the inanimate world around us is engaged in a constant, invisible, and highly intelligent conversation.
It is a profound shift in how we will interact with our environment, and it is driven entirely by the invisible geometry of the antenna. Thank you so much for joining us on this deep dive. Keep questioning the hidden mechanisms that power your devices. Keep looking for those high-value strategic niches, and keep exploring the unseen technologies shaping the world around you. We'll catch you on the next one.